Hello everyone, this is Dr. Lennon, and today we're going to talk about infinite series. So infinite series are a sum of a collection of numbers that go on forever. So typically the notation would look something like this. You would have the sum of a sub n from n equals some index, let's say 1 to infinity. So this just means you have a bunch of numbers, a1 plus an a2 plus an a3 plus a bunch more, and they go on forever and ever. So you could have a plus a sub n plus an a n plus 1 and so on. They just keep on going and going and going forever and ever. So we are interested in primarily if these things converge. That means, do they go to a finite number or do they diverge, meaning they go to either, say, infinity or negative infinity or something like that. And when that's the case, we want to, if they do converge, we'd like to know what number that goes to. So one of the most interesting cases for us is the geometric series. So the geometric series is one has terms that consecutive terms, let's say with the property that consecutive terms are multiplied by a common ratio. So what does that mean for us? Well, it's just similar to what we had for these sequences. So there's kind of two primary forms. You could have a sequence or a series where r is your common ratio, and the terms are just given by r to some power. So if this starts at, say, 0 and goes to infinity, your terms are going to be 1 plus r squared plus r cubed, and this keeps going forever and ever and ever. And similarly, you could have it maybe not starting with 1, but starting with some other number. Let's say a. So if it started with, say, a, we could have a times r to the n, where we have, now instead of starting with 1, we start with this number a, and then we get ar squared, ar cubed, and so on. This series continues as well. Now, essentially, from sequences, we know that these things would converge if either the absolute value of r was less than 1, because we're going to be multiplying by things that are smaller and smaller and smaller, so eventually they go to 0. So let's see. For our geometric series, we are going to understand the convergence perfectly based on the value of that number r. So let's go ahead and write this down as a theorem. So this will tell us whether or not a geometric series converges or diverges. So geometric series, what are the hypotheses? So let's let a be non-zero. And r be a real number. So basically, if the absolute value of r is less than 1, these things are always going to converge. And we know, in fact, exactly what it converges to. So we know that the sum from n equals 0 to infinity of a times r to the n is going to converge to exactly a divided by 1 minus r. And if the absolute value of r is anything 1 or bigger, you're going to be adding numbers that continue to grow or at least stabilize, and in that case, the series will diverge. So the series diverges. So those are the cases. So we can look at some simple examples and figure out exactly what they converge or diverge to using this simple little series. And a lot of our tests for convergence of other series are actually based on, at least if you looked in the proofs, based on actually comparing to geometric series. So determine if the series converge. So let's look at the series starting at k equals 0, going to infinity of 1.1 raised to the k power. Now, so this one's pretty straightforward. This is going to diverge because r equals 1.1, which is greater than 1. So very simple there. If it diverges, if that geometric ratio is anything greater than 1. B, we could look at the series starting again at 0. Again, these indices are often named lots of different things. They use I, J, K, and doesn't really matter what you label your indices. But the textbook prefers K most of the time. What about this one? Well, it might help if we use a little algebra to rewrite this. Remember, we can actually rewrite this as the e to the negative k. We can write that as e to the negative 1 raised to the k. And remember, e to the negative 1 is just 1 over e. So really, this is the series with a value of r being 1 over e. And we know because e is about 2.718, that 1 over e is going to be less than 1. So we know for a fact that this converges. So what does it converge to? So this converges, again, because the absolute value of 1 over e, it's a positive number, but I'm just writing that because of how it's written in the theorem, is less than 1. So in fact, it converges to one over 1 minus 1 over e, right? E is just our 1 is our first term, because anything to the 0 power is going to be 1. So if you could multiply the top and bottom by e and rewrite this a little more cleanly as e over e minus 1, and if you want an approximation, that's about 1.582, something like that. So that's exactly what that series is going to converge to. Even though you're adding up a bunch of infinite things, it will approach this number just as a limit approaches a certain value when we look at a graph. Okay, let's go ahead and look at one with maybe a slightly different story. So this one, we're starting at k equals 2 and going to infinity, and we have 3 times negative 0.75 raised to the k. Now, one thing that's interesting to note here is that we're not starting with 1. So, or we're not starting at k equals 0. So to use the theorem above, we're going to have to basically take off a couple of terms. But we can say, at least at first, that this is going to converge. So it converges, again, because the absolute value of that negative 0.75 is less than 1. So we know for a fact it converges. So now we want to figure out what it converges to. Well, we know what the entire series would converge to. We know that, so note that if you looked at the series going from k equals 0 to infinity of 3 times this negative 0.75 to the k, this would converge to 3 over 1 minus negative 0.75. So what would that converge to? That would converge to 3 divided by 1.75. So what is going on there? Well, we just have to figure out what those first two terms are and then take them away because they're not included. So what would the first term be? Well, the first term, so the first term, we could call it A0, would be 3 times 0.75 to the 0, which is just 3. And then the second term, A sub 1, would be 3 times 0.75 to the 1, which is just going to be 2.25. Okay, so we need to take away those two terms. So the above series sorry. This is negative 0.75. So it doesn't matter for the first term, but it does for the second. So the above series converges to 3 over 1.75, and then we need to subtract the sum of the other two. So 3 plus negative 2.25, which is just going to come out to, let's go ahead and do an approximation there. So that's going to come out to, sorry, just opening up my calculator here, 3 divided by 1.75 is, and then we need to, in fact, subtract 0.75 more. So this comes out to, if you do an approximation, 0.964. So let's go ahead and write that down. Approximately 0.964. Okay, let's go ahead and talk about just one more kind of series in this introductory lecture. So let's talk about telescoping series. So telescoping series so these don't come up super often, but it's a nice trick to know. So and you should always kind of look for it. So these are series where infinitely many terms cancel, leaving us with only a finite sum. And you actually have to be a little bit careful when you use these things. There's some funny ones floating around where you can group them in different ways so that they can be canceled in different orders. These so-called alternating series are actually a little bit tricky when you have a bunch of positive and negative terms. But well, let's look at a few that you don't have this ambiguous cancellation. So it's good just to see a few examples. There's not really a theorem. A lot of times these just involve some algebra to rewrite the terms so that we can see the cancellation. So let's evaluate the following series. So let's go ahead and look at, let's say, the sum from k equals 1 to infinity of the cosine of 1 over k minus the cosine of 1 over k plus 1. So a lot of times with these, to evaluate, it's useful just to write out a few terms and see if a pattern emerges. So let's go ahead and do that. Basically, this would look like what? The cosine of 1 minus the cosine of 1/2. And then we do the second term, that would be the cosine of when k equals 2, the cosine of 1/2 minus the cosine of 1 over 3. And let's just do one more, so plus the cosine of 1 over 3 minus the cosine of 1 over 4. And this process continues forever and ever. So we can see by looking at the second group, this evaluates to 0. The cosine of 1 over 3 is evaluating 0, and we know there's going to be 1 from the next term is going to be minus, plus cosine of 1 over 4, so that's going to 0. So the whole series evaluates to the cosine, essentially, of 1 So basically what's going on here is this is evaluating to the cosine of just 1 minus the cosine of 1 over k plus 1. So what we want to do is we want to think about these actually in terms of partial series and then take that limit. So let's go ahead and do that. So let me rewrite this. So if we did s sub n pretending like the series stopped, we would eventually have the bunch of other terms, and then we would have we would end up with a minus a cosine 1 over n term, a plus a cosine 1 over n term, and then a minus cosine 1 over n plus 1, because we would get that one extra term coming out. So what the s of n ends up looking like is the cosine of 1 minus that last cosine of 1 over n plus 1. So to evaluate the series, the infinite series, we take the limit as n goes to infinity. So the limit as n goes to infinity of Sn turns out to be the limit as n goes to infinity of cosine of 1 minus the cosine of 1 over n plus 1. And we know the limit, when we take that, we're doing, essentially this is going to become the cosine of 1 minus the cosine of 0. And the cosine of 0 is just 1, so this is the cosine of 1 minus 1, and this is approximately, so I mean, if that's confusing looking, you can put parentheses around this 1 as well. So the cosine of 1 minus 1 comes out to about negative 0.46. So again, don't try and do the entire series at once because it goes on, and eventually there's going to be a limiting term there. So you want to find an expression for the partial sum, and then once you've done that, you want to take the limit of that. So don't jump in too fast like I was kind of doing it first. Okay, so let's evaluate one more. So let's look at the series from k equals 2 to infinity of 1 over k minus 2 times k minus 1. Okay, so it's not clear immediately that this is telescoping, but again, we can look at the method of the partial sums to kind of figure out what's going on. So let's kind of write down what Sn would look like here. So Sn, if we start with k equals 2, did I start the series at the wrong place? I should be starting at k equals 3, yeah. So if you started at 2, you would end up with a 0 in the denominator, and we do not want that. So what does the partial sum look like? Well, if you plug in 3, you're going to get 1 over, so this is just a 1, and then 3 minus 1 is 2, so we get 1/2. What's the second term look like? Well, we're plugging in now k equals 4, so we're getting 1 over 2 times 3, so we're going to get a 6 there. Okay, and then we're also going to get, when we plug in a 4, we're going to get, a 5, we're going to get 3 times 4, so that's going to be 12 on the bottom. And this is not super useful. This doesn't look like a telescoping series. So how are we going to make this into a it does not look like a telescoping series. But we can use a trick that will allow us to actually rewrite this in terms of a telescoping series. So what we do is we just look for a little variable replacement here. So let's let j equal k minus 2. Okay, so if we do that, then our series is not going from 3 anymore. If k was equal to 3, then j would be equal to 1. So our series now from k equals 3 to infinity of 1 over k minus 2 times k minus 1. Well, now we know the series j is going to be going from 1 to infinity. And the first k minus 2 would be j, and k minus 1 is just 1 bigger than j, so that's going to be j plus 1. So now this, in fact, is our series. And now the nice thing about that is you can actually rewrite this into, so this is a very nice trick, we can rewrite this as 1 over j minus 1 over j plus 1. Right, that's just the method of partial fraction decomposition that we used for integrating before, that same algebraic technique. So the partial sums that we were looking at before, we can rewrite in this telescoping way. So now we can look at, say, Sn, and it's going to be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, and so on. So we get all those groups, and again, we're kind of looking at our terms here. We're looking at, sorry, the parentheses in the wrong place. So really the way you kind of, let me just rewrite it the line below. So we can write this as 1 plus negative 1/2 plus 1/2 plus negative 1/3 plus 1/3, and so on till you get to the very last one with your 1 over j. If we're doing the, or technically it would be the 1 over n, right? So we're plugging in n, so we would get a minus 1 over n plus 1 over n, and then we would get minus the 1 over n plus 1 for the very end of it. And everything in the middle cancels, so to figure out our series, again, we're just going to take that limit as n goes to infinity. So our series evaluates to the limit as n goes to infinity of 1 minus 1 over n plus 1, and we know that 1 over n plus 1 is going to go to 0, so this series just evaluates to exactly 1. So that's it for telescoping series. We'll go ahead and look at tests that will allow us to evaluate the convergence or divergence of a bunch of other series in the coming lectures. So we'll learn about the divergence test, comparison test, ratio and root test, and then also the alternating series test.